Hey Judy, I love aeroplanes. Today they're going to help us learn more about interference. Look at the two previous modules to remember: frequency, amplitude, and wavelength. One more thing that you need to remember from grade 10 is superposition. In superposition, the medium takes on a shape that is the combined effect of two or more individual waves. Superposition happens because of interference.
Interference occurs when two waves pass through the same region of space at the same time, resulting in superposition of waves. If two crests meet with one another in a medium, a crest with an amplitude of the two combined will result. The two pulses then continue separately again. A slinky spring can be used to show this beautifully. Have a look at the two individual pulses. Now, we send them along the medium at the same time. Have a look at how large the crest is when the two meet. This is called constructive interference.
If a crest and a trough meet each other in a medium, the two pulses will cancel each other out. The two pulses then continue separately again. Look at the slinky again. Here are the two individual pulses. Now we send them along the medium at the same time. Have a look at how large the crest is when the two meet. This is called destructive interference.
We're going to look at a ripple tank because it always helps to see the effect in water waves. This time, we put two beads into the water and make them vibrate. If we have two sources of waves in a ripple tank vibrating at the same frequency, they produce identical waves that are in phase. If you look carefully, you will see that there are lines formed that come from between the two sources. On some of them, the water is completely flat. This is where the two waves have cancelled each other out. That is, destructive interference. Now, in between these lines, there are lines where the water has quite deep crests and troughs. This is where the waves have strengthened one another. They are regions of constructive interference.
We can explain this by looking at the diagram. The solid lines are the crest and the dotted lines are the troughs. You see where a dotted line meets a solid line? That is a crest meeting a trough. If we draw in a few of these points, you will see that they line up into rows. These rows of destructive interference are called nodal lines. A nodal line is a line joining places of destructive interference.
Now, there is a pattern on the waves in which crest meets crest and trough meets trough. You see two solid lines or two dotted lines meet along that line. Again, if you draw in a few of these points, you'll see that they line up into rows. These rows of constructive interference are called antinodal lines. An antinodal line is a line joining places of maximum interference.
We are at the South African Defence Force Museum at Swartkops Air Force Base. We are going to compare the different speeds of airplanes.
The Dakota is very old and therefore rather slow.
But look at the Cheetah. The Cheetah is one of the planes that managed to go faster than the speed of sound.
The speed of sound is really fast, about 340 meters per second. But some aeroplanes, like the Cheetah, have been made to go faster than that and break the sound barrier.
When a plane travels with a speed lower or equal to that of sound, it is said to be traveling at subsonic speed. When a plane travels with a speed greater than that of sound, it is said to be traveling at supersonic speed. We saw with the Doppler effect that when a source of sound is stationary, it will produce circular waves like these ones. When a source of sound moves at a subsonic speed, the pitch of the sound is changed.
When the source, in this case the fighter jet, is travelling at the speed of sound, the wave fronts it produces are piled up together at the front of the fighter jet. When the jet moves at supersonic speed, the wavefronts pile up on one another behind the jet. The different wave crests interfere constructively and form a very large crest, which is the shock wave. A shock wave is the result of constructive interference of a large number of wavefronts. A listener on the ground hears the shock wave as a very loud bang, called a sonic boom, after the aircraft has passed the listener. This actually happens when the edge of the cone hits the listener's ear.
There's a method that scientists have developed in predicting whether constructive or destructive interference will take place at a certain point. It depends on the distance that the two waves travel before they meet. Remember, the waves are being made at exactly the same time. We will assume that there's a crest exactly at the source. The distance from one crest to another is a wavelength. So crest meets crest, and we have constructive interference. If we look at another point G, the distance AG is a whole number of wavelengths. But from B to G is a whole number plus a half. So now you are at a trough. So crest meets trough, and you have destructive interference. We calculate the difference in the distance traveled by the two sets of waves before they collide. This difference in distance is called the path difference, which can be calculated as BG minus AG .
So, if the path difference is a whole number, you have constructive interference. And if the path difference is a mixed number, it is destructive interference.
Let's look at an example, the one that you'll find in your workbook. The diagram shows two speakers, A and B, emitting sound waves of the same frequency and in phase. The distance between two successive compressions is 100 centimeters. Judy is standing 250 centimeters from speaker A and 350 centimeters from speaker B. Show that Judy will experience constructive interference. Divide the distances by the wavelength to find the number of wavelengths. 350 divided by 100 equals to 3,5 lambda. And 250 divided by 100 equals to 2,5 lambda. 3,5 lambda minus 2,5 lambda equals to 1 lambda, which is a whole number. Therefore, Judy will experience constructive interference.
To describe the speed of the jet, the pilots use the term Mach number. It is named after an Austrian physicist called Ernst Mach. Mach number is defined as the ratio of the speed of the jet to that of sound, where m is the Mach number, v0 is the velocity of the object relative to the medium, and vs is the velocity of sound in the medium. Calculate the Mach number for a jet travelling at 900 meters per second high in the atmosphere, where the speed of sound is 300 meters per second. We know that the speed of the jet, v0, is 900 meters per second, and the speed of sound, vs, is 300 meters per second. After substituting into the equation, we see that the jet has a Mach number of 3. Notice that Mach number has no unit. If you have two speakers in a room, you may find there are certain places where one frequency is a bit softer, usually a bass sound. The speakers are vibrating at exactly the same frequency and amplitude and exactly in time with one another, just like the beads in the ripple tank. Where there are nodal lines, there is destructive interference, and so the sound is softer. We're very fortunate to be at the CSIR wind tunnels today. This is the low-speed wind tunnel, where they test mostly cars.
This is a medium-speed wind tunnel. The air flows through all these big tunnels that you see behind me. This is a test section. A model of a plane is put inside here. Special equipment is used to measure the forces on an airplane.
But it's this high-speed wind tunnel that really interests us today because it goes to supersonic speeds, even up to 4 times the speed of sound. Huge tanks release air into this section here. Small-scale models of aeroplanes are placed in the test section, and once again the forces acting on the aeroplanes due to different Mach numbers are measured. Here are some pictures that were taken in a study like this.
The wind moving over the aeroplane is seen through a filter that turns the different air pressures into colors. This picture shows how the aeroplane experiences a shock wave, which is a huge decrease in pressure in the shape of a cone over the nose of the plane. Well, a while ago, scientists thought particles were particles and waves were waves. But then they found that some very tiny particles have properties of both.
So, does an electron behave as a particle and a wave all at the same time?
Yes. In one experiment, they found that it behaves like a particle, and in another experiment, they found that it behaves like a wave with interference patterns.
To be quite honest, I don't really understand. It just shows you how great our Creator really is.
The combined work of 3 scientists, Einstein, Planck, and de Broglie, led to what is called the de Broglie equation. It states that lambda is equal to h divided by m and v, where h is Planck's constant, which is 6,63 times 10 to the power of negative 34 joules per second. M is the particle's rest mass in kilogram, and v is the speed of a particle in meters per second.
Objects with a very large mass have a tiny wavelength, and so we ignore their wave nature. But objects with a tiny mass, like an electron, do have a significant wave nature. This makes sense if you look at the equation with m in the denominator. If an object's mass is very tiny, dividing by a very small number always gives a large number, so the wavelength makes more sense. Mackay Ntini bowls a cricket ball with a mass of 500 grams, moving with a speed of 27 meters per second. Calculate its de Broglie wavelength.
First, convert the grams into kilograms by dividing by 1,000. Lambda is equal to h divided by m and v, where h is Planck's constant, which is 6,63 times 10 to the power negative 34 joules per second. M is 0,5 kilogram, and the velocity of the ball is 27 meters per second. The answer is 4,89 times 10 to the power of negative 35 meters. This is too small to really have any meaning.
How about calculating the wavelength of a photon of blue light traveling at the speed of light? Lambda is equal to h over mv, where h is Planck's constant, 6,63 times 10 to the power negative 34. A photon has mass 1,8 times 10 to the power minus 45. And the velocity is the speed of light, which is 3 times 10 to the power 8. And the answer is 1,228 meters. This is much bigger. That makes a lot more sense.